Throughout the previous course, we looked at everything we needed to correctly model a given reality in Genexus. In this video, through the analysis of a limited reality, different options are analyzed to design transactions using a set of essential resources and solving a series of real requirements. Let's suppose that a Genexus application needs to be designed for managing the tasks of a library related to the loans of books, magazines, and notebooks. It works with members who can access different reading materials, such as books and magazines, as well as computer equipment loaned by the library. The information to be recorded is as follows. Country. Each country is registered with a unique identifier and its name. Member. Each library member is registered with his or her ID card, name, address, photo, and a contact phone number. Library members must be 20 years of age or older. Author. Each author is registered with a unique identifier, name, photo, and country of origin. An author can have several books published. Book. Each book is registered with a unique identifier, title, date of publication, and number of copies available in the library. It can be a novel, an essay, a poetry book, and so on. Therefore, a book belongs to a literary genre. In addition, a book has an author and a publishing house in charge of its publication. Magazine. Each magazine is registered with a unique identifier, title, date of publication, cover image, and the number of copies available. Notebook. The library's services include loans of notebooks to its members, since many of them are writers and researchers. Each notebook is registered with a unique identifier, its image, and a short description. In addition, its status, available or checked out, is recorded. Loan. The library loans books, magazines, and notebooks to its members. Each loan is recorded with a unique identifier, the date of checkout, member, and due date, which must be automatically determined. All loans are for 15 days. They may include a maximum of 3 books, 4 magazines, and may or may not include the loan of a notebook. Only 1 copy of each publication may be checked out, and it's possible to enter any comments considered necessary at the level of each copy's loan. In other words, a damaged cover, missing pages, and so on. In addition, the date on which a new loan is recorded is always the current date, and it must not be possible to change it. Request for copies, book request. It often happens that certain books are in high demand, and the library decides to request more copies. To this end, it makes a request to the corresponding publishing house. The system must check that book copies are requested from the indicated publishing house. Let's start to analyze this reality. Initially, we can clearly distinguish certain simple entities that we can begin to define, such as, for example, country, member, and author. But first, we should take into account that most of the entities are registered with an identifier that can be auto-numbered, except for the member number, who, as we mentioned before, is registered with his or her identity document. Therefore, we define the domain ID with the auto-number property set to true. We also define the name domain as a character of 20. Let's start by defining the country transaction, with country ID as primary key and country name as a secondary attribute. Country ID is based on the ID domain, and to check that the name is not repeated, we define the corresponding unique index. This same definition is valid for all entities where it's necessary to check that the name is not repeated. If it were necessary to record the cities of each country, because we need to know the city of birth of the author, we could model it as a weak entity in relation to the country, since a city does not exist outside that context. So a second level would be added to the country transaction, but since city is considered a weak entity, it will not exist as a transaction in itself. This means that city ID will not exist as a primary key in any table, and therefore, in order to know, for example, the city of birth of an author, the pair made up of the attributes country ID, city ID, which will be the primary key of the country city table associated with the second level of the country transaction, will be needed. However, since the description of the reality we're analyzing does not include the city concept, we will model the country as a simple transaction. Let's move on to member. For this, we define the member transaction with the following attributes. Member document, which corresponds to the ID card, and therefore is not auto-numbered, so we define it as an 8-digit numeric value. Member name, of name type. Member image, of image type. Member address, based on the address semantic domain, and member phone, of phone type. But in addition, reality tells us that members must be over 20 years of age, so we need their date of birth and age, which should be calculated automatically. So, to the transaction structure, we add these attributes: member birth date, of date type, and member age, a numeric value of 3 digits. How do we calculate the member's age? With the age function, which calculates the age from the date of birth and the current date. So we define member age as a calculated attribute that obtains its value from the following expression. Why do we use the today function instead of the today variable? Because it's not possible to use variables in the formula declaration. To check that every member is older than 20, it's enough to declare the following error rule. It should be noted that we're not considering in this analysis the declaration of rules for controlling basic data entry, such as, for example, controlling that a member is not entered without a name, and so on. Now let's consider the authors. We need to create the author transaction with the following attributes: author ID, author name, and author image. Also, we know that the country of the author must be registered, since every author has a country of birth. Therefore, we add country ID and country name, where country ID is a foreign key, and country name is an attribute that's inferred from that foreign key. In this way, we represent a one-to-n relationship between country and author. Now let's think of the concept of book. It's a strong entity that's also identified with an auto-numbered value, a title, a date of publication, an author, and the number of copies purchased by the library. But in addition, reality tells us that a book belongs to a literary genre, since it could be a novel, an essay, and so on. So how do we model the concept of literary genre? If we think that these genres are finite, a first option we can consider is the creation of an enumerated domain. But the categorization of literary genres has been changing over time, and is likely to continue to do so. So the enumerated domain doesn't seem to be the best option, as changes would have to be made manually, and it would not be scalable. We can consider a literary genre transaction with these attributes: literary genre ID and literary genre name. It's a good decision to define a unique index on the name of the genre, in order to avoid the registration of literary genres with the same name. But the book also requires registering the author and the publishing house responsible for its publication. The author is already defined as an entity, but the publishing house is not. And although it's not explicitly declared, in the analysis, the need to model the publishing house entity arises. So, we define the publishing house transaction with these attributes: publishing house ID and publishing house name. We can also create the corresponding unique index on the name of the publisher. The library also offers magazines and notebooks to its members, so we define the magazine transaction with these attributes: magazine ID, magazine title, magazine image, magazine publication date, and magazine copies to record the number of copies purchased. In addition, there's the notebook transaction with these attributes: notebook ID, notebook image, notebook description, and notebook status. A notebook is available or checked out, so we define the status enumerated domain with these values. Now let's analyze the concept of loan, which is essential in this reality. The library allows a member to borrow a notebook, 3 books, and 4 magazines for 15 days. We then have a one-to-N relationship between the entities loan and notebook, and an N-to-N relationship between loan and book, and between loan and magazine. How can we model it? Let's analyze a first option. We create the loan transaction and define the following attributes: loan ID, loan date, member document, member name, member address, loan return date. The return date is requested to be calculated automatically. A loan is made for 15 days, so we declare the following calculation associated with the attribute loan return date. In addition, a loan may or may not include a notebook, so we add notebook ID and notebook description. But in this loan transaction, notebook ID is a non-mandatory foreign key. Therefore, we set its nullable property to yes. A loan includes several books, with a maximum of 3. So we define a second level to record them, including a loan book comment attribute to record any comments needed at the time of the loan. How do we control that no more than 3 books are entered? We can define a new loan books quantity attribute that counts that amount and then condition that value in an error rule. But the same loan can include up to 4 magazines, so we can define another second level parallel to the book to register the magazines. It's also possible to control that no more than 4 are checked out. The reality clearly describes that the registration date of a loan must always be the current date, with no possibility of being modified. To this end, we declare the following rules. Although the objective of this video is to focus on analyzing the transaction design, we're going to suggest an implementation option so that, when registering a loan, only notebooks that have available status are offered. This implementation can be done from the definition of the transaction itself, and that's why we include it. We're going to remove the notebook description attribute, because we'll disguise the identifier of a notebook with its description. We select Notebook ID and define it as a dynamic combo box, with Notebook ID in the property Item Values, and Notebook Description in the property Item Descriptions. This will load all the notebooks registered, so that only those with available status are offered. We declare the following condition. Although this is not the only way to control that a notebook is available when registering a loan, it's an implementation that can be solved from the definition of the transaction itself. Also, we must configure the empty item property to true, since Notebook ID may not be chosen because it can be null. Another necessary requirement is to know the availability of books or magazines in high demand. We know the number of copies purchased by the library for each book and magazine, but we don't know how many are still available, Can we obtain these values in a simple way and based on the transaction design? If in the book transaction we define a new attribute, book on loan quantity, we can calculate the number of copies borrowed and therefore know the number of copies available. What happens if we associate the count loan book comment calculation with this new book on loan quantity attribute? Will it effectively sum the number of copies of that book that have been checked out? The answer is yes, because the table associated with the transaction where we define the calculation is book, and the table where the calculation is resolved is loan book, since it's determined by the loan book comment attribute. Between both tables, there's an attribute in common, which is book ID, and therefore, it's an implicit filter that Genexus will apply. That is to say, this calculation will return the total number of copies of that book that have been loaned. But we need to know the number of copies currently checked out, so we have to add a condition to the calculation that allows counting the number of copies currently checked out. For this purpose, we consider loans whose return date is greater than or equal to the current date. We can state the following. The server_now function allows obtaining the server's current date and time. The today function could also be used. Can we declare this calculation condition? Yes, because the attribute involved, loan return date, belongs to the extended table of the table where the declared calculation is resolved, which is loan book. Therefore, if we know the total number of copies and the number of copies currently checked out, then we can know the number of copies currently available. So the structure of the book transaction looks as follows. In the same way, we can know the number of available copies of a given magazine. Now we have all the information we need to validate a loan. So let's add the necessary attributes to validate the availability of the copies to be borrowed. Book available quantity at the book level, and magazine available quantity at the magazine level. And we control with the following error rules. So far, we've met the requirements to register loans. But let's look at the form generated for the design we've made. What associated tables are created by Genexus for this loan transaction? It creates 3 tables. Loan, associated with the first level, with loan ID as primary key. Loan book, associated with the book level, with loan ID and book ID as compound primary key. And loan magazine, associated with the magazine level, with loan ID and magazine ID as compound primary key. By defining 2 parallel levels, we see parallel grids in the form. This may be cumbersome for the end user, who may request to simplify the design and manage the information in different, simpler screens. For the current design, Genexus has created the following tables. In particular, let's look at the loan, loan book, and loan magazine tables, corresponding to the tables associated with the 3 levels of the loan transaction defined. Can we propose another design for the loan transaction? Yes. So let's see a second option to model the loan. Let's suppose that the end user has asked us to streamline or lighten the loading of this screen and display the information on 3 screens. A screen for registering the general information of the loan, in which the loan is registered with its date, the member's data, and whether a notebook is included or not. A screen for registering the books loaned, in which the books are registered with the necessary controls already defined. And a screen for registering the magazines loaned, in which the magazines are registered with the necessary controls already defined. How can we do so? The first screen corresponds to the general loan data, so we delete the loan transaction levels and leave the general information with the following rules. The following form is generated. To provide another screen with the book register, we need a new transaction. We call it Book Loan. We want to enter the loan identifier, view its general information, and enter the books. Therefore, the primary key will also be loan ID, and thus a new table will not be created because there's already one where loan ID is the primary key. The way we'll be referencing the same loan entity, and only the table associated with the second level will be created. The book loan transaction then has the following structure with the following rules, and the following form is generated. We'll do something similar to record the loans of magazines. We create the magazine loan transaction with the following structure and the following rules. Before analyzing the generated table diagram, let's look at the tables associated with the transactions created in this proposal. Genexus also creates three tables: loan, book, and magazine loan magazine. Let's look at the table diagram. If we look at the loan, book, and magazine loan magazine tables, we can see that they have exactly the same structure as those generated in the previously proposed design. This means that the difference between both designs is not in the structures generated, but in the screens offered to the end user for managing the information. It will always be up to the end users to tell us which design is best suited to their business. From the database structure point of view, it's exactly the same. But we can also propose a third option for loan modeling. Perhaps we could consider that the library bases the loans on books, and the end user requests a single screen where the general data of the loan and also of the books to be checked out are entered. Then, from another screen, the magazines included in the loan are registered. For this purpose, we consider the loan transaction with the second level to record the books. Its structure would be as follows, with the following rules. For registering the magazines included in the loan, we have the magazine loan transaction with the following structure and the following rules. What tables does Genexus create in relation to these transactions? Three tables: loan, loan book, and magazine loan magazine. Loan and loan book associated with the loan transaction, loan and magazine loan magazine associated with the magazine loan transaction. Let's look once again at the generated table diagram. If we look again at the structure of the loan, loan book, and magazine loan magazine tables, we see that they're the same as the tables generated in the previous proposals. These proposals, then, change the screens offered to the end user, but not the structure of the database. If, instead of prioritizing book loans, priority had been given to magazines, the structure of the tables generated would remain the same. Now, is there any other totally flat option which does not include second levels? If the end user requests simple screens without grids, what can we offer? Remember that there is an end-to-end relationship between the entities loan and book, and also between loan and magazine. We will analyze it for loan and book, and it will be analogous for loan and magazine. Let's consider the following structures. For an end-to-end relationship to exist between them, we need a relationship table with the compound key, loan ID, book ID. We then define the book loan transaction with the primary key made up of loan ID, book ID, and the following structure. Which tables are generated? The same ones we've seen before. At this point, we still have to solve the modeling for the request of new copies of books to a certain publisher. For this, we're going to define the book request transaction, which will represent a request to a publisher with the following attributes: book request ID, based on the ID domain; book request date, with the current date by default; publishing house ID, since the request is made to a publishing house; and publishing house name, which will be an attribute inferred from the foreign key publishing house ID. Between this new entity and the book, there's an end-to-end relationship, since a request includes several books, and in turn, a book can be included in several requests. We've already discussed that there are several design options. Let's add book as a second level in the request. Remember that it's an important requirement to check that the books indicated are published by the publishing house in charge. If we recall the structure of the book transaction, we see that it has publishing house ID as foreign key, since a book is published by a publishing house. Can we also add that attribute in this new transaction so that it's inferred by book ID, and we can check if it's indeed a book published by the publishing house to which the request is made? What happens when we try to add it? Genexus returns an error because the publishing house ID attribute is already declared in the transaction structure, and we cannot add it again. We have a multiple reference problem. We need to make reference to the publishing house concept more than once. So, how can we solve a conflict of this type? By using subtypes. This means to define new attributes with other names that refer to the same concept of the publishing house. But where do we define the subtype? In the publishing house concept referred to in the header, or referred to in the second level? Is it the same? Let's look at the transaction design. The publishing house ID attribute is present in the book transaction structure as foreign key. Therefore, Genexus infers that value from book ID. If then both book ID and publishing house ID are present in another transaction, as would happen in this case in the second level of book request, then Genexus will apply that relationship, and publishing house ID will be an inferred foreign key. So, would it be correct to rename the attributes here to define the required subtype group? No, because we would be removing this relationship, and we would allow the user to add a different publishing house ID value than the one previously defined in book. Let's look at the book request header. Here, the publishing house ID attribute is a common foreign key, which is not inferred from anywhere. Therefore, we can perfectly remove it, define new attributes, and declare them as subtypes of publishing house ID and publishing house name. Then, we'll be able to compare them in an error rule, validate that the requested books are from the indicated publishing house. To complete the requirement, we declare the following rules. Since this error rule involves attributes from both levels, it's a rule associated by Genexus with the second level. Therefore, it'll be triggered for each line. This means that when entering a new book ID, the condition will be evaluated, and if true, the error will be triggered. We've met the requirement. What if we had defined the entire second level as a group of subtypes? We would also solve it, with the difference that, as we analyzed in detail in the subtypes video, although this solution may be less obvious and lead to having to create more subtypes to be able to infer them where needed, its main advantage is that the ambiguity is resolved in the same table that causes it. Could we propose some other option to avoid the definition of subtypes in the two-level transaction? Yes, but we must make it clear that as a working criterion, we always suggest addressing the reference conflict in the transaction that presents it. That's why we've solved it in the book request transaction itself. Okay, we could look at the book transaction and define the subtype group there. What's gained with this? that there is no reference conflict in the book request transaction. But we must keep in mind that if there are queries already defined on book, for example, a book catalog, they will have to be updated because the names of some attributes have been changed. Finally, could the use of subtypes be avoided? Yes, for example, by calling on each line, and before recording, a process that returns whether the book is published by the indicated publishing house or not. The definition of the subtype group is avoided, but a process is invoked on each line to evaluate a condition that can be resolved in the definition of the transaction itself. In conclusion, we should remember that we must always analyze, evaluate the reality to be modeled, and implement the option we consider correct. And for this, it's essential to always work together with the end user who will guide us in selecting the design. Let's not forget that the application must be a support tool for end users to better manage and develop their business.